So today we have the fifth lecture of our course, and we are finishing a big block of lectures that are devoted to tools of machine learning. So we have already considered with you Python. We have considered some libraries, at least NumPy and Pandas. And today we start considering Matplotlib. It's a very technical lecture, I should say. So to be not so technical, I'll try to make a little bit shorter what I would say you about Matplotlib. But before that, I want to tell you some, let's say, less technical details about plotting and about expressing your data in terms of plots, of informational graphics, and so on. The thing is that if you are doing anything, if you are writing some sort of article or whatever you do, in most cases, you will need some sort of plots, images to illustrate your work. And it's really crucial to make them as good as you can. So they should express your ideas and deliver the message you want to show to your readers as clear as you can do. So the first thing I want to start today is about all these graphics, how to do plots, how not to do plots, and what should you do to deliver your message clearly to your readers. And let's start with the examples of bad graphics. So what you should not do when you are plotting some data and when you are showing that data to your readers or to your listeners if you are in some sort of conference and so on. So here are some mistakes. Here you see a plot from, I guess, from New York Times, not sure actually. And if you look at a little bit closer, you will see that something is wrong with that plot. So here is Cooper's hawk population. And if you look at axis Y, you will see very strange numbers, something like 0.06 of hawk. So what is that? What does this number mean? What is 0.06 of a hawk? I guess you see either a full hawk, one bird, or you see, I don't know, two birds and so on. It's really hard to see, I don't know, half of a bird or 0.06 of a bird. And the thing is, it turns out that they really meant to represent the number of hawks that were observed during the spring bird count per party hour. So they were dividing the number of hawks per number of hours they were observing that hawks, and so they got these small numbers. But when you are looking at that plot, you don't understand what do these numbers mean. So this is a bad plot. If you were studying, I don't know, maybe physics or something like that, you probably heard that you shouldn't ever leave your axis without any labels. So you always want your axis to be labeled. And in this plot, if I can guess about the x-axis that it's some sort of years, I can't guess what is it on the y-axis. So never do this mistake. You should always keep your plots somehow labeled. Here's another example. This is the problem we often get when we are considering some sort of bar plots. If you are drawing a bar plot, it's really crucial to pay attention to the range you have on the y-axis. So sometimes it's used actually to manipulate. If you are looking at these two plots, they are representing the same data, the exactly same data. What really happened, you have different range on the y-axis. That's why your plot on the left looks very different from the plot on the right. sometimes you get into this trap unconsciously because, I don't know, you are using some sort of software and the software is changing ranges for you. And it chooses the ranges on x-axis, on y-axis for you. And it can choose the range in a way to show you the difference as clear as possible. But the problem is that you don't always want that. And sometimes it's used well consciously to manipulate, let's say, your opinion and something like that. It's really nice if you see on TV some bar plots that show you that something is incredibly growing. But in practice, if you look at the y-axis, you will see that that growth is some sort of, I don't know, 0.1% or something like that. And here's basically the example. So if you look at y-axis, looking at the plot solely, you will think that something changed drastically. So it looks like the bar on the right is, I don't know, 5 or something like that times bigger than bar on the left. But when you look at numbers that you have on the y-axis, you will see that it's just changed from, I don't know, from 35% to 39% or 40%, so something like that. So it's not a very big change, actually. The same problem here. Looks like you have a very big difference, but the actual numbers say that the difference is not so big. It's just, I know, 77 to 75. It's 2 miles per hour. So it's not such a big difference. But bar plots are showing you something like, I don't know, that the velocity changed two times, but it's not. The real numbers say you that it changed just some percents, no more. A bit different problem that we even see in some, let's say, in some articles. You really can see this kind of problem. It's when people are trying to squeeze too much information into a single graph. So you are trying to plot something. You have a lot of data and you want to show all that data to your readers. But the problem is that when you are trying to squeeze all the data into one image, you will get a whole lot of different lines, I don't know, points whatsoever. And at the end of the day, your graph will be just cluttered. It's very hard to find something in this plot, so nothing can be seen clearly. So that's the problem. So I always tell that if you want to deliver your message clearly, you should check your plots and you shouldn't plot too much information. You should give the exact amount information that you need to deliver your message clearly. If you are getting too many plots, so maybe some of them are irrelevant, maybe you can remove them. Maybe you can get, I don't know, some mean trend from your plots and get just one line, just line of means or line of medians or whatever. So maybe you need some sort of perform some additional calculations and make from a number of different curves. You may want to make, let's say, one curve or something like that. But don't make your plots cluttered because nobody will be able to read that. Some people get, let's say, a genial idea to invert axis. That's really confusing. Here is an example. So when you are looking at this plot, it's really hard to grasp at the first sight that the y-axis is actually inverted for, I don't know, for whatever reason someone did this, and you have some bigger numbers down while smaller numbers are up. That looks really strange, and that will definitely make your readers confused. So never do that as well. Pie charts. Many problems with pie charts, and people often get them wrong. The first problem you see here that the percents on this pie chart they are not adding up to 100%. And that's no good. If you are doing some sort of pie chart, you should always make everything add to 100%. Well, actually, I would even say that you should never use the pie charts, because most cases they are useless and they don't bring, let's say, some nice information. There are different methods to express all that numbers. But anyway, if you do, please make sure that everything adds up to 100%. Of course, they have some sort of, I don't know, some exit poll or whatever. They were questioning some people and collecting results. So probably there was some sort of possibility to give more than one answer. So maybe that's the reason they got all these big percents. But anyway, it's no good to represent them this way. Moreover, a 3D representation is used that makes the things even worse. Why? Because when we look at pie charts in 3D, we have the problem with the perspective. If you look at these two pie charts, you see that we have this sector. It takes exactly 25%. 25% on one pie chart and 25% on another pie chart. But the problem is that on the pie chart on the left, it looks much smaller than on the pie chart on the right. And everything is because of the perspective. So that's why you would rather never use 3D pie charts, because they are confusing. Of course, if you additionally forget to set some numbers on that pie chart, that will be even more confusing. And when you are doing some sort of graphics, so of course, the first thing is to represent your data clearly, but please try to let's say, refer to common sense and to good taste to make your plots more or less, let's say, digestible. So don't use any fancy fonts or acidic colors. Of course, this is the photo from, I guess, Large Hadron Collider when they were announcing the discovery of the Higgs boson. So yes, even they sometimes do very ugly presentations. But please don't make presentations as as LHC, or how that collaboration is called. Here is a small video. I'm not sure how it will play out. I'll try to start it, and you will see some, let's say, some story about plots and how to do them and how not to do them.
A toothpaste brand claims their product will destroy more plaque than any product ever made. A politician tells you their plan will create the most jobs. We're so used to hearing these kinds of exaggerations in advertising and politics that we might not even bat an eye. But what about when the claim is accompanied by a graph? After all, a graph isn't an opinion. It represents cold, hard numbers, and who can argue with those? Yet, as it turns out, there are plenty of ways graphs can mislead and outright manipulate. Here are some things to look out for. In this 1992 ad, Chevy claimed to make the most reliable trucks in America using this graph. Not only does it show that 98% of all Chevy trucks sold in the last 10 years are still on the road, but it looks like they're twice as dependable as Toyota trucks. That is, until you take a closer look at the numbers on the left and see that the figure for Toyota is about 96.5%. The scale only goes between 95 and 100%. If it went from 0 to 100, it would look like this. This is one of the most common ways graphs misrepresent data, by distorting the scale. Zooming in on a small portion of the y-axis exaggerates a barely detectable difference between the things being compared. And it's especially misleading with bar graphs, since we assume the difference in the size of the bars is proportional to the values. But the scale can also be distorted along the x-axis, usually in line graphs showing something changing over time. This chart showing the rise in American unemployment from 2008 to 2010 manipulates the x-axis in two ways. First of all, the scale is inconsistent. compressing the 15th-month span after March 2009 to look shorter than the preceding 6 months. Using more consistent data points gives a different picture, with job losses tapering off by the end of 2009. And if you wonder why they were increasing in the first place, the timeline starts immediately after the US's biggest financial collapse since the Great Depression. These techniques are known as cherry picking. A time range can be carefully chosen to exclude the impact of a major event right outside it. And picking specific data points can hide important changes in between. Even when there's nothing wrong with the graph itself, leaving out relevant data can give a misleading impression. This chart of how many people watch the Super Bowl each year makes it look like the event's popularity is exploding. But it's not accounting for population growth. The ratings have actually held steady because while the number of football fans has increased, their share of overall viewership has not. Finally, a graph can't tell you much if you don't know the full significance of what's being presented. Both of the following graphs use the same ocean temperature data from the National Centers for Environmental Information. So why do they seem to give opposite impressions? The first graph plots the average annual ocean temperature from 1880 to 2016, making the change look insignificant. But in fact, a rise of even half a degree Celsius can cause massive ecological disruption. This is why the second graph, which shows the average temperature variation each year, is far more significant. When they're used well, graphs can help us intuitively grasp complex data. But as visual software has enabled more usage of graphs throughout all media, it's also made them easier to use in a careless or dishonest way. So the next time you see a graph, don't be swayed by the lines and curves. Look at the labels, the numbers, the scale, and the context, and ask what story the picture is trying to tell.
Okay, so here we have it. Hopefully now you'll not be deceived by some wrong graphs if someone will try to represent it to you. And hopefully you will not draw something like that on your own. So be careful with that. Okay, some sort of few tips to use just to make your plots a little bit more beautiful, let's say. Don't use too much colors in your plot. So 3 colors, it's more than enough. Don't use more than 2 fonts. So too many fonts, they make them, let's say, all these plots, they make them ugly. Try to use so-called modular grid. So if you are trying to place number of different plots, different graphics into one image, it's really nice idea to create, first of all, some sort of modular grid and say that in this place I will put my plot, here I will put some drawing, there I will put some text, and so on, and only then start putting all that elements into your general image that you will present to everyone. Try not using 3D. If we are doing some sort of scientific presentation, it's much more easier to draw all that plots and to understand what do they mean when they are just 2D. So try not using 3D. And to choose some sort of nice palettes of colors, here is the link for a tool for you called Color Brewer. It's used, I guess, I don't know, by some sort of people drawing maps, and it will help you to choose some palette, some colors that look nicely together. So that may be helpful as well. Okay, so I showed you how bad infographics looks like. Now I want to show you some examples of good infographics. So how do we plot nice plots? How do we make them understandable and make people just grasp in one glance what is on your plot? So the really the best plot you can make, it's when, I don't know, it's when your reader just takes one look. It's like that neural network, YOLO. You only look once and gets all the information he needs just with one look. So he doesn't need to, I don't know, refer to different parts of the image to search something in text and so on and so forth. Just look at the plot and understand what message are you trying to bring to him. So here is an example. a historical example of a really nice infographics. It's one of the first Playfair's trade balance time series chart. It was published in Commercial and Political Atlas in 1786. And here, just looking at that plot, just think about it. 1786, it was really, really long time ago. And here, looking at this plot, you see that he made everything he could out of it. So just looking at it, you understand what is happening, where you have balance in favor of England, when you have balance against it, and so on and so forth. Really nice. Charles Joseph Minard, 1869, diagram of Napoleonic France invasion into Russia. This graphic is really notable for the fact that it's represented in only 2 dimensions, 6 types of data. So if you look at this plot, you will know the number of Napoleon's troops, distance, temperature, the latitude, longitude, so where they were traveling, how many people he had, and so on and so forth. So it's really nice plot, and you can find it as an example of good infographics in many different books. Some more historic or geographic example. So here you see some imaginary landscape. So artist has put all the waterfalls he knows into one image. And it really helps you to compare them. So if you want to know which one is the biggest, which one is, let's say, comparably small, and so on and so forth, you can just look at this image and you can grasp immediately all the information that you want. The same example with rivers and lakes, so you can immediately compare them by length and so on. So you can find the longest river in Europe, in Asia, in Africa, and so on. You can immediately say whether rivers in Africa are generally longer than rivers in Europe, and so on. And one more example with mountains. So you can look at this imaginary landscape with mountains, and immediately you will see which mountains are really high, which are not so high, and, well, perform some comparison between them. One more nice example from modern days. This is NASA or GPL past and present missions that flew all around the place. So looking into this plot, you can immediately see which planets we were able to get to and how many missions did we have. A little bit more historic example. So it's Austro-Hungarian Empire railway network. It's 1912. And here you can see not only the map of the empire and the railways, but you really get some sort of coloring of this map that will tell you how much time do you need to get from Vienna to any other part of the empire. So just looking at this map, you can immediately guess how long would it take for you to take train from one place to another. So it's really, really nice map to have. Here is an example of representing many plot distributions. It comes from modern instruments, so I guess you can draw that in Matplotlib. And this is an example how to, let's say, avoid some sort of going into 3D, but instead place them all into one plot. And it's really nice technique because you can immediately compare all that distributions and understand what happens when some parameter changes. In this case, you have parameters, some sort of months, and you have distribution of the mean temperature on the x-axis. Yes, I have a question.
Yeah, but we have z-axis here, and what is it? There is no name for it, but it's clearly there. The histograms, they have a height. I mean,
that's distribution. So we have a label here that tells you that this is some sort of distribution of temperature. So it's let's say the probability density of having that temperature in some month. So you are getting some month, you have some plot for that month, and this plot will tell you if I don't know, if you have some temperature 75 degrees of Fahrenheit, what is the probability density of having that temperature. And yes, in these cases, it's really nice to have some labels that will immediately describe of what are you plotting there. So yes, it should be somewhere written that it is a distribution. Okay. So, by the way, we are doing all these lectures. We will move to some different part with the next lecture and do some more math and so on. But anyway, you will see a lot of ways of representing data throughout our course. So I will use, of course, I will use some sort of plain text because I'm trying to do all that collapse like complete and containing all the information I'm giving to you. You will see some code. Code can be used to represent some ideas. Moreover, in some cases, you may want to write some sort of pseudocode to represent what are you meaning and what you want to show to your colleagues. Of course, some formulas, pictures, all the kinds of plots. So we will see some histograms, some scatter plots, and so on, and even videos. So presentation of your, I should say you that presentation of your work is really important. So don't be lazy and try to choose right instruments and communicate your results clearly. Because even if you have performed some really nice work, it's a little, let's say, it's a little bit meaningless if you cannot communicate that to anyone, because you can share that new knowledge you have obtained with your scientific work to other people, and it will just remain with you and no one will know about it. So it's not so good. So you should learn somehow to communicate your results and to make other people understand what have you done and what are the implications of whatever you have performed. So it's really crucial. So try not neglecting that part. Yes, of course, the main point is that you should do some good work, but anyway, you should be also able to represent it to others and make that as clear as possible. Okay, so a few more examples before we get, let's say, technical. These are examples from different, let's say, sources. So here is some plot from NY Times, New York Times. What I want to show you with this plot, when you are creating some sort of infographics, it's nice to have in mind some, let's say, checkpoints and to go through all of them. So first of all, so the first checkpoint is so-called know your audience. So when you are creating all these infographics, you should think who are the people you will present these data to, and different people will need different, let's say, different plots. This is an example from New York Times, and it's really good for New York Times. So to represent it to anyone, but you will probably choose not to use this sort of plots in a scientific article. How do you think why?
It's hard to tell the exact number for the lower parts of the plot.
Yes, absolutely correct. So it's really hard to tell some sort of exact numbers. So if you are doing this plot for a scientific article, so probably your colleagues will want to know what are the exact numbers and make some calculations and so on. So you will not want to make this plot into a scientific article, or you will need to accompany it with some sort of table with exact numbers.
Mm-hmm. Could you like add some axes? It would probably help.
Maybe yes.
Numbers are so small, it probably won't help much.
Maybe adding some grid or something like that may alleviate the problem. But anyway, for scientific articles, you will need to somehow rework this plot and change something in it to make it suitable for a scientific community. For general audience, that's perfectly okay. So nobody will check all the numbers and some sort of reconsider them. But for scientific article, it's no good because scientists want numbers. They would like to check that numbers and so on. I guess I will skip this example. It's a little bit, it gets too much into biology. Let's look better at this one. So your plots should not depend only on the public you are presenting to, but it should you should think about the technical way you will represent your plots. So here's what I mean. You see two plots of some sort of trajectories of particles. The left plot may be good for let's say some article that you will read in paper. But if you are presenting with some sort of projector, so you are doing some sort of presentation, this plot will be barely seen. So it's really it's really not so clear as you may want. So you can't see clearly all the lines and so on. So probably if you are doing some sort of presentation and you are showing that on some big screen or whatever, you may want to remove some of the lines, just leaving only some crucial trajectory that you want to present and so on. So you may want to remove some details to make your plot a little bit clearer. Once again, don't forget about captions. They are not optional, they are needed, and do not trust the defaults. I told you about the defaults when you are plotting some sort of bar plots, because your tools can choose for you range along y-axis, so on and so forth. And you may think that you got something when there are really small changes. And here is an example when you are plotting some data with default Matplotlib and when you are trying to do some sort of styling. Of course, you won't do that when you are calculating something just for you in most cases because you don't have so much time. But when it gets to preparing some sort of article for scientific publication, or if you are preparing to some sort of speech somewhere in a conference, for example, or whatever, you will definitely want to make your plots prettier and to put all the captions needed on that plots. Use colors effectively. So using too much colors may make your plot not only look uglier, but it can even hide some sort of message that you want to show. So this figure, it represents the same signal whose frequency increases to the right and intensity decreases towards the bottom. And it uses 3 different color maps. And if you see that rainbow and seismic color maps, they are bad for this representation. But if you use only one color, it's really clearly seen what is happening here. So going on with the frequency of your signal and what's going on with its amplitude. One more interesting example. So I already told you about bar plots, and here is the example with disk sizes. So sometimes we want to represent some numbers with let's say disk plot, and the problem is that you may choose at least two different ways to convert your numbers into disks. Which ways are that? How do you think?
Area and radius.
Yes, absolutely correct. So you can choose radius to represent your number, or you can choose area. And if you see in these two plots, they look very different. They look really different when you use radius and when you use area. In most cases, humans perceive the size of the area. So if you use radius, you are some sort of exaggerating that difference that you have in your data. Of course, if you are doing some sort of scientific things, I would rather recommend you to use some numbers, not to confuse people at all. So just put some numbers and they will understand what do you mean. But anyway, if you decide to use these sort of plots, please remember that we human perceive size as, in most cases, as the area of something, not its radius and so on. That may be deceiving. And of course, avoid so-called chart junk. I have already told you about too many lines in one plot. If you are trying to squeeze everything you have into one plot, you will be, most cases, you will end up with something like this. And you definitely cannot understand what is happening right there and what all these lines, what do they do? What's that? So in many cases, you will need to redo your plot or find some different ways of representing your data to deliver your message and your ideas clearly. Here is one of the possible examples on the right. When I'm trying to represent each of the subplots that I have with some sort of bold line, and all the rest are made, let's say, some dim. And at least something is seen here. But anyway, I think, well, depending on the meanings of that data, you will probably find some other ways to represent it and to make everything clear. And here is the last example. I called it "Message Trumps Beauty." So first of all, the first thing you should think about is the message that you are giving to your audience. Everything else is, let's say, you can beautify your plot a little bit later. This plot is, let's say, a little bit ugly. But anyway, it delivers the message that the author wanted to the audience. So at least it does its job. So that's okay. Good. How much time do we have?
For the break, around 15 minutes.
15?
20.
15, 20.
Okay. Okay, so
to be exact. So it's called 20.
Okay, that was everything about plots. So now I'm planning to get to considering Matplotlib, and I'm just thinking, do we start now or do we make a break and consider this part after?
If you think that we will finish earlier today, then maybe it makes sense to make the break earlier as well. Okay, so I guess we can make a break, I don't know, 5-10 minutes, whatever, and then I will proceed to considering the functions from the library, a bit more technical part that we have today. I think I'll be very brief on that part because you probably have already grasped the idea how to work with that libraries and that you need to consider documentation all the time. Then let's continue at 11:10. Okay. It's 8 minutes. Okay, so
we will continue 11:10. So let's get to more technical details. And today I will tell you about Matplotlib. That's a library to create different plots, and you will definitely want some plots in your scientific works and so on and so forth. It's really good because it's easy to use and easy to get all that plots when you are working with Python. And here are a few examples for you. What can Matplotlib do for you? Of course, you can't remember everything that I have in here. I myself don't remember all that functions and so on. So you will need to refer to documentation when you are working with Matplotlib all the time. But I want to show you at least to do some sort of overview of its abilities, so you at least know what's in there, what you can expect from Matplotlib, and what you may do with it. And then if you need to do something like that, you will go to the documentation and find out how do you call all that functions and which functions exactly do you need. So here is an example how to start. You are just importing, so you can import Matplotlib, or you can import submodel of pyplot, so matplotlib.pyplot. As you see, in most cases, I will use some sort of shorthands like PLT and MPL, so not to write all that long names like Matplotlib. And it's really handy. Here is an example of plotting, something really simple, like sine and cosine functions. So here I have x. It's just an array of numbers. So I have a lot of numbers that signify which points along x-axis I'm interested in, and then I calculate the value of the function at that point, and then I pass everything to function plot of Matplotlib. And as the first argument, I say, so here are my points along x-axis. Here are corresponding points along y-axis, and it creates some sort of graph for me. So here you see that example. You can save your plots in files. Really nice ability to have, because most cases, of course, you will not only want to see that plots yourself, but you will want to show them to someone. So it's really nice to have them in some sort of in form of some sort of image. There are many file types you can use. So here is the list. So like PDF, you can use in LaTeX. So if you are compiling something in LaTeX, you can use, you can save your pictures to PDF and immediately be able to, let's say, import them into your text files. Of course, you can use something less fancy like PNG or GPG formats and so on and so forth. Okay, regarding Matplotlib itself, one thing to make you, let's say, unconfused, so one thing that may make you confused is that part that Matplotlib has, in fact, two interfaces. It was started as some sort of substitution for MATLAB. So one of the interfaces is a MATLAB style interface, or I like to call it, let's say, stateful interface. The other one is more like object-oriented interface, and I call it stateless interface. What do I mean by that and how it looks like? Let's check MATLAB interface. So here you have that PLT that I have imported, so all that Mario, and I am calling some functions from it. Depending on which function I call, I change the internal state of that submodule, and the result of the operation depends on that internal state. So that's why I like to call it stateful. So it has some state inside it. So here's an example. I'm switching to some subplot So I want to have few different plots in one image. So I create some subplots, and I'm switching to one of them, and I'm telling to plot me, let's say, sine function. Then I'm switching to another subplot, and I'm telling to plot me cosine function. As you might see here, I get the exact result that I want. I have two subplots, and I have sine and cosine functions. What I want you to pay attention to, please note, I use the same function plot with basically the same arguments in both cases, but I got my curves for sine and for cosine in different subplots. Why? Because before that, I have called a function that changed the internal state of the library in a way that it knows that whatever you do next, it should output that into the subplot number 1 or number 2. The other interface it has, it's object-oriented interface, and I would rather call that stateless. So here I am creating subplots. I'm getting some names, fig and x, with and connect some objects to them. And then I'm working with, let's say, this object x, which represents Matplotlib axis. As you see here, I have, let's say, a list of that objects, and each of them represents different subplots. So to make different plots, I am referring to different objects, and I am using them, but I am not creating some sort of internal state in the Matplotlib. So these two are different approaches to the same problem. So how to plot something and how to use Matplotlib. What I want you to ask at this point is some sort of philosophical question. So we have these two approaches. Of course, not Matplotlib only. When you are creating some sort of system, so you are thinking about your own modules, you are writing some code and so on, you're free to choose any approach you want. And you may want to choose either stateful approach, either stateless approach. How do you think, what are the pluses and minuses of each of these approaches?
First is simpler, kind of simpler, maybe.
Yes, it's a bit simpler. So you don't need to create some additional variables and do some manipulations with them.
Second, maybe more, maybe there are more things to do with objects, like more opportunity. We have maybe more opportunities to modify something or work with something.
Well, let's put it this way. Stateful approach is a little bit dangerous, because you have some sort of state inside of your library, and you are not definitely, you have no warranty that someone would say didn't influence that state somewhere or something like that. So it's a little bit of a problem.
Also, in my opinion, it's a little bit easier to mess up because I've always found those subplot arguments just some magic numbers that you never remember what each one of them means.
Yeah. So you can really mess up, because you can even forget on your own. So what comment did you do, and in which state right now is all that library? So maybe you did somewhere subplot and you forget about it, and then you are trying to do some plotting and it plots somewhere else, and you don't understand what's happening with all that stuff. So yes, stateful approach is a little bit simpler. It's simpler to implement, it's simpler to use maybe, but it's of course simpler to mess up with that. So probably if you will create some sort of your own system, so project your own classes, so and so on, you will choose between these two approaches, and it's really nice to have, I don't know, some idea which one is better in that exact scenario you want to use it. So if it's something really simple, maybe stateful approach will be okay. If it's too bad, if you, I don't know, mess up somewhere, or you are doing some really complicated system, so maybe you should retreat to stateless approach and get, I don't know, all that object-oriented stuff. Okay, some abilities of Matplotlib. So here I'm creating just an empty grid, nothing fancy. I'm doing plotting. You've seen that already. If I call function plot a few times, I will get few plots in my image. And that's okay. I can style a little bit my plots. So here is an example of using different colors. You can define colors in many different ways, starting with some sort of predefined names like blue, green, red, some shorthands like G for green, doing grayscale, hex code, I don't know, RGB, and so on and so forth. So many different ways to define colors. That's great. You can use different line styles. A really nice feature to have. Moreover, if you are planning to do some sort of article in a scientific journal, in some cases, they are published in black and white. So you can have only some sort of grayscale there, but you can have green or red or blue color and so on. And in these cases, you may want to use different line styles to make your lines look different. So yes, it's a good feature to have. Here is an example how to use different shorthands to make lines of different color and different style. That's simple. You may want to adjust your access limits. Really nice feature to have as well. So functions xlim and ylim will be helpful for you. So they define some sort of minimal and maximal value for x and y's. This is a very simple example, but there are many cases. If you have some sort of plot and you have many points, and one of them is some sort of outlier. So it's somewhere out there and it messes up with your whole plot, because if you are trying to squeeze everything into one image, you just get all the other points, I don't know, lying on one horizontal line, and this one point is just outstanding. But if you make your limits, some reasonable limits, you will see how your points really behave in that plot. Here is an example with reversing axis. I don't think you will ever need that, but you have that ability. You can make the different positions for your numbers and so on. So different styles. You can change aspect ratio and so on and so forth. So you may want to choose, you may want to check the documentation and see which functions do you have and how do you use them. Labels. Of course, we don't forget labeling our plots because we want reader to know what exactly are we plotting. And functions like title, xlabel, and ylabel will be very handy for you to unconfuse your reader. What kind of curves does he see in your plot? Legend, really nice feature to have. If you have a number of different curves in your plot, you may want to create a legend. It's created a little bit, let's say, strangely. So for each line you draw, so here I'm drawing them with function plot, I can give them a label, but you won't see this label anywhere in your plot until you call function legend. Legend collects all that labels, puts them into one, let's say, rectangle, and basically writes the names and labels the curves you have in your plot. Here is the second example using more OP way. Basically the same thing. Scatter plots. You may want to grow just separate points. So maybe the the curve itself does not have any meaning, but the individual points have. So you want to draw some sort of scatter plot, and here you have this example. I'm using here the same function plot, but I'm using a different style, and this style tells me, so don't draw all that curve, just put some sort of points. Of course, you don't need your x's and y's, y's, not y's, but x's, you don't need them to be increasing when you are doing that sort of plotting. And here is an example when I'm using just some sort of random numbers, and it still draws you points in that image. So that's pretty okay. So that depends on the meaning of the data you are representing. In many cases, we will have axes as different features, let's say. So I can have all the possible combinations and values for one feature and for another feature. And of course, I will have just some sort of points, not a curve in my plots. There are different markers, so you can use different markers to make your points distinguishable. So let's say you have data set A and data set B, and it's some sort of points in, let's say, two-dimensional space. So you have two features, and you want to represent them in plot to see how do they behave, how do they look like, and you may want to choose different markers to show which point belongs to which data set. And of course, once again, you can create legend that will tell you what's happening right there. So which is which. You can use both lines and dots with plot function. That's okay. You can style your markers very heavily. So here's an example. Once again, there is no need to get right now into it very detailedly. I just want you to know that you have that abilities. And if you will wish for that, you will need for that, you can always refer to the documentation on Matplotlib and find out how to do that properly. So these are just examples for you to know that there is such an ability, and you can do that with Matplotlib. But of course, no one can remember all the parameters and so on. So you will need, at the time you will need this functionality, you will need to check documentation how to get to it. Scatter plot, that's a separate function for just drawing some sort of dots in your image. Of course, you can use that as well. So here is an example that just represents some sort of points from sine wave or something like that. But you can change some styles. You can change sizes of that points and so on. And this is the way you have, let's say, additional dimensions in your plot. So here's an example when I'm not just setting some dots in there, but I'm choosing sizes of that dots. So basically, it's not dots, it's some circles. And moreover, I'm even adding some sort of color. So in this plot, I'm representing at least 4 different dimensions. So 4 numbers are squeezed into 2-dimensional plot. And you may want to use that in many cases because, of course, we can draw anything beyond, well, basically 2 dimensions. We can try to draw something 3-dimensional like, and even succeed with that, but there are some subtleties. But drawing some 2-dimensional picture, it's definitely okay. You can always do that, and you can And if you need to add some more parameters, you can use colors and you can use sizes. The same example, but with existing data set, so-called iris data set. These are some sort of flowers, iris flowers, and someone has measured some lengths of petals, some lengths of something else, and we can represent that data just in our plot with few lines of code and show with different dimensions what are the sepal width, sepal length, and so on and so forth. Okay. For large data sets, PLT plot should be preferred over PLT scatter. So it works slower, so you may retreat to PLT plot. And the reason behind that is because PLT scatter has the capability to render a different size and color of each point. So renderer should do some extra work. So if you don't need that extra functionality, you may want to retreat to PLT plot for large data sets. If you need that functionality, of course, then you probably will use scatters. Okay, so what's this? Basic error bars. You can not only draw some sort of plot, you can draw it with error bars. Really crucial for some sort of scientists who do experiments, because we can never get the exact result. We always have some error bars, because all the measurements, they are performed with some sort of error. It's impossible to measure something exactly. And here is an example of drawing that error bars. It's performed with function that is called error bar. So here is the functionality, you have it. You can draw continuous errors. It's done a little bit more complicated, but you still can do that. Here is the function fill between that is used to draw all this gray area. So if you are doing some sort of math or whatever you do, and you need to show that your curve is between some other curves, you can use this fill between to show that that area in your plot. Density and contour plots. This functionality we have here as well. A really nice tool that will help you to represent 3D data with two-dimensional plotting. So yes, in some cases, we want to draw 3D as, let's say, 3D. But in some cases, it's preferable to use some sort of projection and draw all these lines, as you see here, in this contour plot. So all these contours, they represent some sort of function and some value this function has. It is constant along all these lines. It's performed with this function called contour, and you are passing few arguments into this function. So it's a grid along x and y axis. So some points you have along x and y. Where do you calculate the value of the function you want to represent? And v represents basically the values of the function you have calculated along that mesh grid, along x and y. In this case, it's some sort of sine, cosine, well, something very randomly chosen. Of course, you can use some color maps to make your plots a little bit more expressive. So here you see with the red and gray color, you can clearly see which areas are higher, let's say, than other areas. You can look at this plot as some sort of projection of 3D of a plot in 3D onto 2D. So just projection. Here are some more examples, styles. So you have many different possibilities to change style. Here's one interesting example when you are writing the exact values of the function along that contour lines. So you can do that as well. Histograms. In many cases, you will want to draw some sort of histograms to, I don't know, to process some statistical data. So you have a lot of measurements and you want to know at least something about the distribution of that measurements. I will show you a little bit, let's say, better and more advanced method as we progress through our course. So probably we will learn something about so-called KDE, kernel density estimation. And this KDE will replace the method with histograms and so on. But anyway, in many cases, they will suffice. And as the first thing to do, you may want to check how it looks like just by creating some sort of histogram. And here are examples. How can you do that? Just calling the function hist, and you get your result just right away. Of course, you can do some sort of styling, change some colors, and so on and so forth. Here is an example of plotting few histograms. So if you have different measurements and you want to somehow compare the distributions you have, so you can do that right away. You can, of course, do two-dimensional histograms. Here are a few examples. So it's really easy to do. You can customize not only plots, but your plot legends. So here are some examples when you are, I don't know, changing location of your legend. You can do that. You can turn on and off frame in that legend. You can do some more things. So here are a few examples. I'm just showing that. Legends. Well, here is much more styling, but if you wish, you can do, let's say, your custom legend and put some sort of even graphical objects into there. So here is an example. You can use multiple legends in your plots. Not sure why, but maybe you will want that at some point. You can use color bars, few more examples. So you can create some plot, and then you can call function color bar that will show you this small thing to the right. And you will have some sort of reference which color corresponds to which value. It's really nice to have. There are many different color bars in Matplotlib, so here are they. You see them and how do they look like in grayscale. And why we are concerned about grayscale, it's because in many cases journals are printed in grayscale, so you may want to know how do your plots look like in grayscale, because someone may read them that way. Of course, we don't have that problem in internet, but anyway. Here's an example of changing that color bar and so on and so forth. What else do I have? Function imshow. In some cases, you may want to use that. You are passing a two-dimensional numpy array to that function, and you have an image produced. So here's an example of drawing some of the digits from so-called MNIST data set. And you may want to use this function in many cases if you are processing some images and you want to output what exactly are you processing at some point. Some more examples with color bars. You can create multiple subplots in one plot, so that you have seen already. What else? You can put some text and annotation in your plots. So here is an example when you are putting some text. So maybe you want some points to be emphasized. Of course, you can transform that text in many ways, and so on and so forth. These are a bit more complicated examples, but I just wanted to show the picture so you know that you have the ability to create something like that. When you need it, once again, refer to documentation and you can find out how to do that. Okay, what else? One more styling. That's okay. Yes, different styles. So you can use here is the classic style, or you can change something by hand and restyle your plot as you wish. So here is an example. How much can you restyle it? You can change some default parameters and so on and so forth. Here are some standard styles you can use. So here is PLT style. You can create context and draw something in that context. So here are examples of different styles you can use and how do plots in that styles look like. And of course, you can plot some three-dimensional things. I won't use it very much throughout our course because we don't have any ability to interact with that plot, at least at this point. I don't know why, but in Colab, they just don't work. But when you do plotting on your own machine, you will probably get interactable plots and you will be able to move them, rotate them somehow, and so on. Here I can just produce some sort of images. So for all 3D plotting, I will be probably using Matplotlib library. So most cases I'm using Matplotlib library. It seems a little bit ironic that I'm teaching you Matplotlib, but drawing everything in Plotly. But that has perfect reasons behind it. I want my plots, at least some of them, to be interactable, and Matplotlib does not give me that ability in Google Colab. And I still wish to use Google Colab because that makes me sure that all the data I'm sharing with you, you can perfectly run it and you will see the same result as I see in my machine. Well, because it's performed on Google servers, so every time I get the same result. So here is some sort of trade-off. But anyway, the standard is using Matplotlib, so I will still show you how to get that. So here are examples of 3D plots. Well, not telling much about it. You can just look at them. You can see functions like plot surface or plot wireframe. So depending on the situation, you may want to use some of them to draw your plots. You can do some sort of surfaces. You can draw scatters in 3D. So that's all the abilities you have. Here is a more advanced example when we are performing some sort of triangulation of points. And here I'm able to draw a Mobius strip for you. This is interesting because you can represent that as a function of x and y. So you just can't create function f from x, y that will make a Mobius strip for you. So you need some additional abilities of your plotting library to put some 3D points into that. Some examples with base map. I'm not sure if you will need that, but I saw that, well, some people use that this library. It's called base map. It has ability of drawing maps for you. So you can draw a map. So here is an example. And you can put something into that map. I don't know, some points, some scatter plots, so whatever you want. I'm not getting into all these details. So if you want, you can check out the documentation on the base map. But I just want to show you some abilities of it. So it can draw different maps for you with more or less details. So that depends. And you can put some data onto that map. So here is an example. I took the map of Ukraine, and I have and I tried to add into this map some points that represents big cities of Ukraine. that we have. And sizes of these, well, it's not points, it's rather disks, some sort of disks or circles. I represented with their size the area of the city, so you clearly see like Kiev in here and so on. And with their color, with the intensity of the color, I'm representing the population in some sort of logarithmical scale. So here I'm using base map to represent some geographical information, and just looking at the map, you are able to see some big cities of Ukraine and estimate how many people there live, so on and so forth. Some styling with Seaborn. Yeah, I guess I should tell you about that at the end. So if you wish to make your plots a little bit prettier, because default parameters of Matplotlib, so many people consider them ugly. So yes, that's the case. And these people even created some sort of library to make your life easier and to make some styles for you. So for example, library Seaborn, you can use function set, and you can pass, I guess, some style into that set. There should be some examples down there. And it restyles your plots, or let's say it changes that internal state of the Matplotlib library and makes it look like quite different, and I guess a little bit better. So here are examples of different kinds of plots after you have performed all that SNS set, and you see that they changed a lot. Okay. What else do you have? Styling. Well, I guess that's probably everything I have for you for today. So let's do some sort of wrap up. So what did we learn today? So except that it's nice to draw nice images that represent your idea clearly and may help you deliver that idea to others. We have considered some sort of good graphics and some sort of bad graphics. So I hope that now you know how not to draw your plots, how not to confuse your readers, and how not to fall in a trap when someone tries to confuse you with all that sort of bar plots and so on, with changing the limits on axis and so on and so forth. So now you're aware of all that things, so probably it's for good. And I showed you the abilities of the Matplotlib library, and now I guess you have at least some image in your head what it can do for you. And in future, when you will need to draw some plots and to make some graphics for, I don't know, for some article, if you're writing some scientific article, or you are doing some presentation, or whatever you do, you will know that Matplotlib can do that for you, refer to documentation, and create some nice, clear plots that will deliver your message clearly and, well, help you somehow. I guess that's all for today. If we have some questions or comments regarding anything in this lecture, please.
Okay. Can we make some animations with Matplotlib? Animated plots?
I guess there was such ability, but I can tell you off the top of my head. I'm not sure. Okay. I can definitely do something in the other library. In Plotly, there is the possibility of creating some sort of small animations, let's say so. I guess there should be something in Matplotlib. But you should be aware that in Colab, you will probably not able to do that, because if you can't even, I don't know, rotate some 3D plots, there should be some problems with interaction with that. Or maybe they have fixed that, I don't know. So.
does have animation, but I don't know how it works in Colab.
Okay, yeah, so we have animation there, but we need to check, does it work in Google Colab?
And why Matplotlib possibly better than Matplotlib?
Well, the reason to choose one over another may, let's say, differ. So why did I choose Plotly over Matplotlib when creating these lectures? Well, I was starting at 2019, I was starting creating these lectures. And at that point, definitely, there was no ability to create some interactive plots with Matplotlib in Google Colab. But it was possible to do that with Plotly. So at that point, I thought, well, if I need to show you just some sort of plot, so the main idea is to show you the plot and to make it more or less to interact with that plot, why don't I just use Plotly? So it was really nice idea. It can work with Python, it can work through JavaScript and so on and so forth. So I chose that library over Matplotlib. If I had the ability of interacting with plots as I have in Plotly, at least at those years, I would definitely choose Matplotlib. Because Matplotlib is now some sort of standard in the industry, and if you are going on some, I don't know, if you are going to be some sort of data scientist and so on, people will expect from you to know how to use Matplotlib. They won't expect from you how to use Plotly, but they will expect from you how to use Matplotlib. So, so that depends on your goals. So what do you want to get at the end of the day? If you need to do something in Colab, you will probably prefer Plotly. If you need to do something in some different, I don't know, on your own computer with Python installed on your computer, you may prefer Matplotlib. So that depends.
So overall, like Matplotlib is must use like more often than some other.
Yes, it's well used in industry, and probably if you get into that industry, everyone will expect from you that you know how to use Matplotlib.
Understood. Got it.
Okay, anything else? No? Okay, if we don't have any more questions or comments, then we'll see you at next Friday.